For our Project 3, we decided to expand on Project 2, replacing the Telare 6004 CO2 sensor with a K-30 sensor having a range of 0 to 10,000 parts per million compared to the Telare 6004's range of 10 to 2,000 parts per million. We also included the use of a GPS, so that way we will be able to plot our CO2 values as a function of latitude, longitude, and altitude. In addition, we have the velocity at any given point throughout our journey thanks to the GPS. Here we have a picture of our circuit as well as a fritzing diagram of our circuit. We included a resistor on the enable-disable for the GPS just to support the load without having too much current going through there. We also added two 1 microfarad capacitors, one between the 3.3 and ground voltage supply for the GPS, and the other between the 5 volts and ground for the K-30 sensor to stabilize the power supplied to both of these sensors in the event that the current is not enough or the power just gives out. Here we have the Arduino code, thanks to Dr. Bensky, Kyle, Caitlin, Spencer, and Clayton as well for working with the GPS before us, because that helped a lot. So part of the Arduino code involved feeding the GPS data. Now, because we had it rather long, looking through all the data within a loop, we had multiple feed GPS steps to just keep checking to see if new data was coming in. And that managed to work out all right. We had quite a bit of trouble for a while reading to the SD card, but once we plugged the capacitors in and had it with a better voltage supply, it was all working out great. And then we also have our MATLAB code, which we were using to plot our GPS and CO2 data. Here we just have a short clip showing our powered circuit. You see the LED on the SD card on the SD shield lit up, meaning it's getting power and writing data points. And we also have a short clip of the K-30 sensor with its blinking LED, signaling that it is also receiving power. And thanks to Dr. Bensky's takedata.org referral, we were able to plot our data points on Google Maps/Google Earth. And we can click on any individual data point and see the time, relative CO2 level, latitude, longitude, altitude, and miles per hour. Now, the reason why we're calling it relative CO2 level is because the sensor placement no longer has a hose pointed directly at the exhaust. So while in Project 2 we were easily topping out at 2,000 parts per million, in Project 3, since we don't have that hose lead, it's just sort of picking up extra CO2 levels rather than a direct blast from the exhaust. And the reason why we had to do this was because we were running into problems with the hose leads melting, since the hose leads are smaller on this K-30 sensor than they were on the Telare 6004 sensor. So this was the data run from Wednesday, and we have the close-up ending in the parking structure with the data value there. And then we have the data run for Tuesday, coming back home in the afternoon. Here we have our route plotted in MATLAB on latitude and longitude, which we just wanted to confirm was indeed the same that we were seeing on Google Earth. We have Tuesday in blue, Wednesday in red, with the starting and end points plotted in green and black, respectively. So you have one start and one end point by each other from each of the runs. We used MATLAB's plot3 function to get a three-dimensional plots generating latitude, longitude, and altitude, so you can create a sort of visualization of the path taken in all 3 dimensions. But for easier understanding, we have the 2-dimensional plot of altitude and latitude, seeing how altitude changed as a function of latitude, since latitude was pretty much just increasing or decreasing for each respective run, while longitude had periods where it would increase and decrease on the same run, and that's a confusing longitude to altitude plot. So the beginning of the latitude altitude plot shows Cal Poly above 120 meters, with my house resting a little bit over 60 meters to the far right of the plot. Similar to the altitude versus latitude plot, we have the relative CO2 levels versus latitude plots, because it's easier to follow with respect to latitude for the same reasons as for the altitude. And as we mentioned earlier, the levels of CO2 are much lower compared to Project 2 because of the placement of the sensor and the lack of hose leads directly in the exhaust gas line of fire. We also have a plot of altitude differences, velocity differences versus relative CO2 differences. This plot was generated taking the altitude, velocity, and relative CO2 emissions at one data point and subtracting it from the next data point. This is to generate the next plots, which we see the altitude difference versus relative CO2 difference. You see that at an altitude difference of 0, we have a much greater spread of CO2, relative CO2 differences compared to the velocity differences, which are all mainly centered and 0 with a few outliers. The velocity difference to relative CO2 differences, meaning that if we're staying at a relatively constant velocity, but we begin to drive uphill or downhill, you would see a corresponding increase in CO2 emissions or decrease in CO2 emissions to maintain that constant velocity. With the velocity and altitude differences, we see a strong relationship between the two, mostly centered on when velocity is 0, you see an altitude. When a velocity difference is 0, you see altitude changing. When you see altitude difference of 0, you see velocities changing. And that's attempting to maintain a constant velocity throughout the trip. There are, of course, some outlier data points, but for the most part, they follow along. They're all along across. So here we have the average values for velocity, altitude, and parts per million. Now, as expected, the average value for velocity is close to 50 miles an hour, and that has to do with the fact that for the vast majority of the time we're spending the route on the freeway, and the speed limits on some of the off-freeway roads are also relatively high. And the concentration in CO2 values being in several hundreds is also expected, with the standard deviations extending the concentration ranges down to 200 and up to about 600 parts per million. Now, we'd expect this to be much higher right in front of the exhaust, but since the sensor is spaced off to the side, these values are expected to be lower. Here we have our statistics. So we have the average differences for miles per hour, altitude, and CO2 values, and we have the standard deviations for each of these values for each data set. And we see pretty much similar data samples for each. Now, the average altitude difference, the reason why there's a noticeable change between Tuesday and Wednesday is because, as mentioned earlier, we have that fact that Cal Poly is about at 120 meters while my house is at 60 meters. So the Tuesday afternoon trip is me coming home, which is why we're going to have an average altitude difference of positive, since we're essentially going more downhill throughout the entire trip, and the way we were calculating differences was taking the next data point, was taking the current data point minus the next data point. So what would be a negative altitude difference then becomes a positive altitude difference, which is why we have the average. And subsequently, we get the flip side of that for Wednesday, because that's mostly going uphill. Standard deviations are pretty much what you'd expect. The altitudes are relatively close together for most of the trip. So apart from when we get to Cal Poly and when we get close to my house, they're all pretty much around the same level. Same with the velocity. Now, afternoon is generally rush hour, which is why it's quite a bit slower compared to the Wednesday trip. And CO2 levels are pretty much the same if we're going by the square root error rules. So we found a study which shows that old model cars was would have different emissions based on altitude level, with higher altitudes corresponding to higher emissions. However, for the current model, which is, I have a model 2006 Prius, we see is at that third red circle overlapping the pink and blue lines, which means that there's almost no appreciable effect due to altitude on the emission levels, which is backed by the data that we see having no real correlation in CO2 parts per million levels as a function of altitude.